Okay, welcome for those of you joining us on YouTube for watching the recording after the event has happened. My name is Matthew Egbert. We're going to have the inaugural Artificial Life Seminar Series kickoff today with a talk by Hiroki Sayama. What we're going to do now is just hang out for another couple minutes and wait for a few more people to join, let the technology issues sort themselves out. And then we'll get started. So thanks for joining. And if you want to, feel welcome to skip ahead a little bit in the YouTube video so that you don't have to watch us waiting around for the technology. Cool. So it looks like we've got a good turnout here. Lots of people.
Wow. How many?
I see 1, 2, 3, 4, 5, 6 different icons, but I know that at least one of those is supposed to be a group of people. And I think that there's more than I can actually see on the screen here.
Oh,
yeah,
okay.
I start scrolling. And there's
no, the pressure building up on my shoulder.
The pressure's on.
Yeah.
If I can just thank Hiroki while we wait for doing this talk, I think that it's really cool that
thank you
we're
very
seeing
much.
this. And I think that the topic is really interesting.
Thank you very much. Thank you for allowing me to use this kind of ridiculous title for this talk.
Well, it's nice to have different types of forums for different types of talks, isn't it?
Yeah.
They don't all have to be exactly the same type of scientific presentation. And sometimes there's a kind of talk that you want to give that you can't really give anywhere else, and maybe this series can provide a place for that a little bit.
Yeah.
Okay, so it's 10 o'clock now, and I think what I'll do is just run through a couple of announcements before we actually get going with the talk. The first announcement I want to make is that we're looking for volunteers that might be interested in hosting or chairing some of these seminars going forward. So this is going to be a monthly series, and we've got people lined up for the next 4 months or so. And it would be great not only to have a variety of different speakers, but also a variety of different hosts, people that are willing to bring different types of material to the seminar. And so on. So if you're interested in playing that role and being a host, or if you're interested in being a presenter, then please feel encouraged to get in touch with me, Matthew Egbert. You can find me by Googling me or by way of the seminar series website, no problem. For those of you that want to participate in this seminar or a future one, there's really 2 ways to do it. One is to click the Jitsi link, which is on the seminar website, and that allows you to be present and at the actual seminar and to be able to ask questions using your voice rather than your keyboard. And I encourage you to do that if you possibly can. But these seminars are going to be taking place all over the world. With speakers in different locations, and that means different time zones. So it's going to be pretty common for many of you that the time zones won't work out for you. And in that case, you can watch the talk after the fact on YouTube. And you can also participate in the conversation is the goal. So if I share my screen here, I can show you where, if we look on the ALIFE Virtual Seminar Series website, here's the page for Hiroki's talk. And if you scroll down to the bottom of that, then you can see down here, there is a discuss sort of forum area where you can ask questions, make comments. And what we'll try to do is encourage the speakers to check back in, at least for sort of roughly the week after the talk, and be able to respond to questions and comments that people make there. So just because you're not participating in the live session doesn't mean you can't participate and ask questions. So I encourage you to do that. Let's turn off my screen sharing here. The other thing is, for those of you that are participating in the live session, there's a way that you can raise your hand. So Hiroki is going to give his talk, and then afterwards, there's going to be some Q&A. And if you want to ask a question, Hiroki said, if you want to ask a question during his talk, you're welcome to do that. I will try to keep my eye out for those of you who are tempted to ask a question. Instead of immediately unmuting your microphone, it would be great if you could click on the raise your hand button, which is in the lower left hand of your screen if you're participating on Jitsi, and I will try to track that and ask you to ask your question at the right time. Okay, I think that's it from me for announcements. So I will turn off my screen and turn on Hiroki's. And if you don't mind, well, so to introduce Hiroki, many of you already will know him. Hiroki Sayama is the director of the Center for Collective Dynamics of Complex Systems at Binghamton University. He's a professor in the Department of Systems Science and Industrial Engineering. He's an avid tweeter of artificial life topics, and I enjoy being friends with Hiroki on Facebook because he's very generous with his updates and doesn't just tell us when he's had successful grant applications or paper acceptances, but he also tells us when he's been frustrated by the system and when things haven't quite panned out, and that's helpful to see as a sort of junior academic. But with no further ado, it's a real pleasure to have you here, Hiroki. Thank you for agreeing to give this talk, and apologies in advance if we have any issues with any of the technology. Hopefully not. But just before we get kicked off, if you wouldn't mind, I thought it would be kind of fun and interesting to ask you which was the first artificial life conference you went to, or one of the first that you remember, or if you have any recollections about any of that.
Cool. Okay, can you hear me now?
Yes.
Okay, good. First of all, thank you very much, Matthew, and anyone else who would be involved in this seminar series. I think this is a great initiative for the ISL and for the community, and it's my honor to be the first speaker for this virtual seminar series.
Thanks very much.
Your question is about what was my first exposure to the ALIFE conference, right? It's 1996 when the ALIFE first went to Japan. I don't think most people attending here they remembers that event. That's when Chris Langton was still around. He was coming to the conferences. So my first ALIFE was the ALIFE 5, I believe.
Okay.
That was held in Nara, not in Tokyo, but Nara is an old historical town in Japan. So I got my poster accepted. So that was my first time.
Awesome.
But I was involved heavily in artificial life research for many years, even before that.
Okay.
So even though Matthew introduced me as the director of a complex system, blah, 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 I'm basically a lifer. So I wouldn't say this outside, but this is my community. So I can say I'm pure a lifer down to the bottom of my heart. Yes.
We'll have to edit that out of the YouTube video.
Oh, yeah, it's okay. It's okay. It's true. And everybody who actually grew up in this field, they go out to the different area. They put different hats, pretend to be the expert in different domains. But what you are doing, what I'm doing is the crazy stuff, right? So we are basically spreading our culture, the weird culture, to the different fields. I think that's what we should do.
That's great. Yeah. And what a great segue to the title of your talk as well.
Oh yeah.
The best paper in my career, which has been cited only 4 times so far. So tell us about that. And then we'll have some Q&A afterwards.
Okay. So let me begin then. Yeah.
Great.
So I was actually very honored to see this email coming from Matthew that you actually mass emailed a bunch of people about this seminar, right? So I was reading this, and then just to start with some really minor issues, as a non-English native speaker, I didn't know this word, inimitable. So I think this is a middle school level word, but I never seen this word. So I looked it up, and I found this definition: the impossible to copy. Basically, this is the N as the prefix to negate the imitable, right? And this actually made me crying because no, this is not what I'm supposed to be called, because today's talk is all about this. Okay, so you guys have seen this film, right? Yes or no?
I have not seen it, but I know.
Okay, come on. So please watch this. This is all about Alan Turing, the imitation game. his whole life, including, not whole life, but mostly covering his career in second half of his career as a code breaker. But the underlying theme of this film is all about imitation, right? So the adjective inimitable is not appropriate for this. I'm going to blame Matthew for using this word. So I'd like to convince everybody that imitation is actually the very important topic. And basically, the paper I want to bring up in this talk is this one, Construction Theory, Self-Replication, and the Halting Problem. I believe every scientist has her or his own best paper or most favorite in his career. This one turns out to be mine. It was published back in 2008 in the journal named Complexity, not even the Artificial Life journal, but this one tries to connect the fundamental issue of artificial life back to Alan Turing. And when I put the title of this seminar, they are only cited 4 times so far, I was hoping that by the time when I give this talk, people would realize, oh, hey, this is a cool paper, maybe I should cite, and the citation count might have gotten up by now. But I checked yesterday, still 4 times. So the ambitious plan is, by giving this talk, I would like to artificially manipulate the citation count for this my best paper. So that's my ambitious goal. Okay. So this paper, even though this is trying to connect Alan Turing back to the artificial life, it starts from this person. Everybody recognize this face, I hope, right? So this is John von Neumann, genius and polymath, one of the biggest scientists of the last century. And in the ALIFE context, we often discuss him as basically the father of artificial life. Even though Chris Langton is the father, he founded the field. In his introductory material, he often refers to John von Neumann's the fundamental question that he asked later in his career. So von Neumann asked this question: looking at the natural biological system, evolution always tends to increase the complexity from really simple unicellular organisms like a bacteria to very complex form like the humans or the mammals or animals. And compared to this empirically observed trend, most of the artificial system, all of them actually, all of the artificial system tend to show the reduction of complexity through evolution. For example, in order to build a car, you need to have a much bigger complex system like a factory and the gigantic, cooperative organizations to produce this already complicated, the product. But if you look at the trend of complexity, they don't really go up. They always go down. So that was the original question John von Neumann asked. He wondered, can artificial system made by humans make product that's equally complex to itself or more complex than themselves? So his answer, and this is a very famous one, the self-reproducing automaton theory, he showed by example, if the artificial system is made of a description of itself and a machine that builds the product written in the description and make a copy of them and combine them together, then this is a self-reproducible machine. And that can be producing the equally complex machinery from the artificial system. And if there is any mutation or any kind of variation added to the description, there is a potential that the complexity can go higher over time. So that was a theoretical work. He published some book chapter back in 1948, almost like how many years ago? 70 years ago. And then later on, as many of you know, he designed a specific example of such systems using cell automata, 29 state, 4 neighbor cell automata. So here's his basic design, even before going into the cell automata design. He created a machinery made of the description I and the mechanism to produce the product, which is A, universal constructor, and description copier, which is tape duplicator written here. It's a B, and the coordinator or controller. And if you combine A, B, and C together, this is the automaton D. And then you put D's own description to here, and then this is the self-replication. represented logically on the right. Okay. So this was the theoretical background. And yeah, so this is the complete self-replication. You put the description of A plus B plus C, like a chemical reaction. The result is the duplicates of the both machines and the instruction. So that's the basics. And here I would like to connect this von Neumann's framework about the self-replicating machines that is often considered to be the beginning of artificial life, 1948, back to even older stuff that connects back to Alan Turing. So rewinding the tape from 1948, about a decade, this guy, okay, Alan Turing, not the Benedict Cumberbatch, but the real Alan Turing, really nice looking guy. So he is probably most well known in computer science, at least in theoretical computer science, on this paper on computable numbers with an application to the some word that I can't really pronounce. This is basically a fundamental problem in mathematics. David Hilbert, they proposed this problem as one of his famous 1900 paper, whether or not the mathematics can prove its soundness or completeness by itself. Okay, and Alan Turing was still very young when he was publishing this paper in 1936. He was even before he obtained his degree. So he was not, like in the early 20s, I believe. So this is a paper that proposed the famous Turing machine and also the universal Turing machine and its fundamental limitation by proposing the halting problem. So if you haven't had a chance to read this paper, by all means, I highly encourage you to read it, especially if you are a computer science related researcher, because this paper is unusual. Because this was written in the younger version of Turing, it almost reads like a blog. It's not really a pure mathematics paper, so you can see very casual, intuitive description here and there, and that kind of creativity is very fundamental when he produced the idea of Turing machines, in my opinion. So anyway, so my main theme is how could this be related to artificial life? Because we usually don't talk about Turing's this paper in the ALIFE research. And probably Turing's work is more well known in the ALIFE community for his other work, reaction diffusion system and Turing pattern formation. That is much later than this one. So anyway, for those who are not really familiar with theoretical computer science, I just want to give a few minutes of review. Turing machines. Turing machine is a theoretical machine. It's a model of a human computer. You have the finite state automata here, and then this machine has access to the infinitely long tapes that can be rewinded and move forward, going backward. This is controllable by this finite state machine. And this machine can also read and write symbols on the tape, move left and right. And it has been known that this is a universal computational device. Any kind of human computable or machine computable process can be computed by Turing machines. Okay, and a more important thing that Alan Turing showed is that you don't really need to have the millions of different Turing machines. You just need to have one Turing machine, one specific Turing machine with a specific instruction set that can read the instruction to behave like any other Turing machines. So this is the idea of universal computer. Or maybe I can also say that this is the moment when the humanity realized the possibility of the idea called software. You just need to have one hardware and you write the software. The hardware behaves exactly what you intended. So that's the groundbreaking moment in the history of any kind of artifacts. I would say before this moment, every single task was done by the machine, specifically designed for that particular task. But after the universal Turing machine's invention, we realized that we don't really have to do so, at least in terms of computational tasks. All right. So anyway, I would like to point out the similarity between this universal computation framework and what John von Neumann later proposed, the construction framework. Turing machine is about the universal machinery that can execute any computational tasks that's specified in the finite description. Okay, And similarly, and I'm pretty sure John von Neumann get inspired by Turing's work. He created a universal constructor that can execute any constructional tasks. That could be called as construction theory, similarly to computation theory as we know, even though the word construction theory is not really popular. And of course, there are some differences. We are not so naive to say they are identical. There are some differences. For example, Turing machines, universal computers must be able to perform any logical mathematical tasks. But this doesn't apply to universal constructors. Universal constructors have limitations and a well-defined set of objects that they can construct. As long as they can construct anything that is inside that set, that is called universal. And the other way of difference is that universal constructors are always assumed to be made of the same parts, same materials that they are made of. Okay, sorry, they are operating on, and therefore their behavior is constrained by the same physics as what is being produced. This is not necessarily the case for universal computers. Universal computers can be in the hardware, manipulating only the software materials. So those are some differences. Okay, and there is one more logical difference, and this is more fundamentally linked to the artificial life research. This is the design of the John von Neumann's universal constructor. And when we try to identify which part corresponds to the universal computer proposed by Alan Turing, there's only one part, universal constructor A. This corresponds to universal computer in Turing machines. And all the other parts, like a tape duplicator, controller, and all other stuff, this part, at least in my understanding, people usually don't consider this as the critical part that could also exist in the universal computation in Alan Turing's sense. So my main topic, my main focus of this talk is that is actually not true. These tape duplicators and controllers, they also show up in the theoretical computer science, especially in Alan Turing's original paper that people don't really pay attention to much. So this part actually is there. So the rest of the talk is to illustrate how Alan Turing actually used this idea in his original proof. Okay, and this is where that correspondence appears. The halting problem. Again, I don't assume that everybody is theoretical computer science, so I should explain what it is very briefly. The halting problem is a very well-known mathematical question, which can be written in a very intuitive way. Here's a halting problem. Let's assume you want to develop a software that receives another computer software and then decides its behavior. Does this program stop eventually, or does it fall into the infinite loop? That's one question. Or you can just say, does this software behave exactly as written in the specification? So that's another version, which is mathematically equivalent. So basically, the halting problem is to predict the behavior of the given computer program, which would be a very variable tool if they exist. So the question is there any such general procedure to solve such a prediction problem for any arbitrary computer programs and inputs? And it's well known, it's not possible. Okay, and Alan Turing actually proved this is not possible in his paper. So here's a really quick proof, because the details of proof actually matters in this talk. So let's assume there is a universal Turing machine that let's call it M, this one, that can solve the halting problem somehow for any program P and any input I. So in this case, the output should be 0 and 1. If this machine decides that the program P stops on input I, then the output would be 1. Or if this machine decides that this program P does not stop on the input I, the output will be 0. But in both cases, M itself always holds. All right? If such a machine is possible, then you can modify that machine a little bit so that you can create this kind of diagonal situation. This is the revised version. It receives only the program P, and then considers P as both a machine or the program P and the input given to that program. This is a kind of weird setup. But in this case, you can still get the halting problem solved. If P stops on the input P, then the output will be 1. If P does not stop on the input P, then the output should be 0. Still, this machine M dash always holds. Okay? And if that machine is possible, you can also tweak a little bit so that this kind of weird situation can be possible. If program P stops on the program P input itself, then this machine artificially is made to fall into the infinite loop. So that M star, which is a modification of M prime, never stops if P stops on P. Otherwise, it says, well, P does not stop on P, so you put 0. M star stops. Okay? Now getting really mathematically complicated. And with this setup, you ask one question. What happens if you ask M star what is going to happen if the input program P is M star's description itself? Okay, this is really the mind-boggling the thought experiment. You have to consider very carefully. If P of M star stops on P of M star, this is precisely the situation when the M star does not stop. Or if M star does not stop on M star must stop. And then you see a very carefully crafted contradiction in both cases. So this contradiction proves that the original assumption was wrong. There is no such Turing machine that can be used to solve the halting problem for the general input P, general program P and the input I. Okay, too much. But this is a typical textbook proof when someone wants to understand why the halting problem is not possible. Okay. However, and this is the really cool stuff. However, I said this is a textbook proof. Turing did not take this path, and this is where the artificial life idea comes in. The Turing's original proof did not use that kind of the strategy, and instead, this is what he said. This is the exact copy and paste from his paper, and this is how he can be considered very creative, open-minded young researcher. This proof, by the way, this proof really means that the negation. So he already knew the textbook approach that by introducing the artificial negation in the proof, it will be very easy to show that the halting problem is not possible. But he said, although perfectly sound, has the disadvantage that it may leave the reader with the feeling. This word shows up in mathematics paper, feeling that there must be something wrong. Therefore, he said, the proof which I shall give has not this disadvantage. And he went on to some details of what kind of stuff he did. And this is the too much amount of text. But basic idea is this. He didn't really use any negation in his proof, but instead, he asked the machine, what is going to happen? This is essentially what he showed in his original paper that no one talks about. His proof actually shows that the second machine, M dash is the machine that received the program P and asked the halting problem on the behavior of the machine P on the P itself. He questioned what is going to happen to this machine. Okay. So if M dash receives M dash's own description as an input, we can actually study what is going to happen. So Turing proof goes like this. The system M dash, this is the machine, and the P of M dash, this is the description of its own, tries to compute the behavior of the Turing machine described in P of M dash. This is basically the itself. All right. So what this machine is doing is to compute a situation written as M dash plus P of M dash. This is exactly the same situation it is in the real physical world. So he pointed out this is a circular self-computation, and therefore this produces, even though he didn't say self-replication, he implied that there is a replication process that goes on and on and on inside the Turing machine's tape. So this is how he showed that this is impossible. So the visual illustration is like this. So here you have the actual Turing machine M prime that tries to solve the halting problem. And if it receives its own description, this is the configuration of computed M. This is the computing M. This is the virtual representation of computed M. It goes like this. Inside it's like the movie, The Inception. You go into the dream, you go into another dreams inside the dream, and inside dream and dream. And as you consider this situation, you see that the replication takes place in terms of the levels of nestedness. And this is exactly what he pointed out. This is called a circular computation, which never comes back. It's like a limbo in the Inception. You fall into the limbo and the computation never comes back. And that's how he showed that the halting problem is not possible. And I thought this is quite interesting, although it's not really well articulated in either the theoretical computer science or artificial life community. And this actually illustrates how deeply the John von Neumann architecture of self-reproducing automata is related to his Alan Turing's proof. Tape duplicator and controller, they have the counterparts. So this really means that you are diagonalizing both the input and the machinery. So in Turing's proof, he showed that given the program P, you put the P as both machines and the inputs. This operation corresponds exactly to what John von Neumann did. Okay, so to interpret the parent and offspring, this relationship in the Alan Turing's framework, the parent corresponds to the computer. And in the meantime, the offspring corresponds to the computed. So this is real, and this is in the tape of the parents. But this matching actually gives us a lot of implication about what is happening in the self-reproducing system. So computer computes the computed, but if we do that same thing in the construction theory, the parents produces offspring. Okay, so that means that the solving the unsolvable question, in this case, it's a halting problem. So it's really to determine whether or not the process eventually stops or not. So if you try to attempt solving this question in the construction theory, that basically creates an endless circular process of self-replication. And that might be the one potential interpretation of what's happening in the biological life. So here's a visual illustration. We have seen this sequential process of self-replication in the attempt to solve the halting problem. We can also consider this as a biological process. The original ancestor just tries to execute the instruction given inside its genome. What happens if I execute this instruction? This has been realized physically because now this is the construction theory. The result of the construction does exactly the same thing. What happens if I execute this instruction that keeps going on? This is logically identical to the previous slide. So this, I think, is a very deep connection between the theoretical computer science and the fundamental issue of artificial life. Okay, to summarize, the similarities between construction and computation that has not been paid much attention, I think that has a fundamental, foundational contribution to the beginning of artificial life. And even though people don't really discuss the Alan Turing's famous paper is a foundational beginning of artificial life, I think there is a very interesting connection there. And specifically, what I propose is the von Neumann's self-reproducing automata model has a fundamental connection to the Turing's original proof, not the textbook proof, but his original intuitive proof of the undecidability of the halting problem. So undecidability really means that this implies that it's an endless process. If something is decidable, it is guaranteed that it will be an end. So if the living system, life, is to solve the decidable problem, maybe billions of years ago, life ended already. but the life somehow continues up till now. So that must mean that the life is trying to solve the undecidable, unsolvable problem. That's why life can continue. So here's my punchline. So we might be considered as we are all inside the endless self-computation construction process initiated billions of years ago by a first universal constructor, whose objective might be just try to see what's going to happen if I execute this instruction. And we are now in all the deep inside the limbo, like billions of layers of simulated, computed process. That's it. So here I just put my corrected adjective. I'm imitable. So please imitate what I do. So if you imitate my thought process, I hope that the citation count is going to go up from 4 to 5 by tomorrow. Thank you very much.
Awesome. Thanks very much, Hiroki. That's a great talk. Yeah. So we'll give people a moment. I said at the beginning of the talk that people should use the raise their hand button to ask questions. But I think that actually might be a bit difficult because I can't see any of your names, so I can't actually call on you to unmute yourself. So if I can just ask people who have a question to unmute themselves and interject at an appropriate time, that would be great. We can do Q&A that way.
Okay.
And just to start off the Q&A, I have a quick sort of comment / question, if that's all right.
Yeah.
Which is to say that I think it's really neat to draw out the similarities between these different systems, right? So you've got the universal constructor, you've got the universal Turing machine, and then you've also got life, and you're finding these parallels between the three. But I also think it's really interesting to pick apart the differences, I suppose. So in particular, I'm thinking about this idea of decidability and trying to think about that in the biological context. So that's a very important part of Turing's argument and an essential thing about thinking about the limits of computers and computation. But I don't see an exact parallel in living systems, right? Where what would decidability be? So in the Turing idea, there's an answer that's ultimately being striven for, right?
Yeah.
But I don't know I don't see a parallel there in life. Do you see one, or do you think that's maybe where the metaphor doesn't?
So perhaps the word decidability may be a little bit misleading, right? So in biology, especially when you are they're looking at only the replication process, it's not about deciding something, right? Rather, I would say when someone is producing the offspring, the task, from the theoretical viewpoint, the task being solved is to try to see the outcome, final outcome. What is the final outcome of this instruction when I execute these biomolecular construction process? What is the final outcome? Well, I got 2 sons. I have the offspring, but that's not the end of the story because they are also developing. They are also reproducing. So my computational task is not ended yet, right? Because the product is not final. So when is the final product? I have no idea. They might have their kids. That is still part of the product of the single construction process. And if that continues, my answer will never be obtained. Does it make sense? Yeah. So that's kind of the mathematical analogy. I know this is a crazy idea, and it may not have any utility to help us better understand biology or any other computer science issues, but that's one way to reinterpret the reproduction process as a computational process. So in that sense, deciding whether or not the process stops or deciding what is the final outcome, final, quote unquote. So that's my interpretation.
Cool. Yeah. Okay. Yeah. Thanks for that. Yeah. Does anybody else want to jump in with a question? I'll give you another moment to build up the courage in case you do. So with that in mind then, Hiroki, you had a slide that looked at the limits of Turing machines. It was early on. It was maybe, I don't know, around slide 6 or something like that. Looked at the sort of constraints or the limitations of them, of Turing machines and of universal constructors. Maybe slide 16?
This one?
That one or the one after it?
This one? This one?
Yes.
Do you still see my slide, right?
Yes, I do. Yeah.
Okay. Yeah. Okay. So, this is it.
Yeah. Can you elaborate on that a little bit? I just wanted to, if you could draw that out a little bit more.
Oh yeah, yes. So the universal computers have a very rigorous mathematical definition, right? So any algorithmically computable task should be able to be computed by using the universal computers. So this is actually a very high level requirement. But when John von Neumann defined the universal constructor, he didn't have that kind of expectation. All he wanted to say is that any kind of patterns in cell automata that can be made of these building blocks should be, constructible. So that's the much weaker version of the universality. So that's what I mean by this slide. Okay, but in the meantime, universal constructors must operate within the same space.
Yeah.
But the computer can exist in this space outside the tape.
Yeah.
So the computational side has a much more freedom about the actual architecture of the system, but the constructor side has a lot more constraints in terms of how the constructor should be built.
Yeah.
Those are two main differences.
So I know that, like, with von Neumann's work, there was this real clear distinction between the information, and you made the same distinction, the description and the machine, right? There's the machine, and then there's a description of the machine. And in the Turing machine, there's the instructions, and then there's the code that they operate upon, and that's I don't know. I guess I just need to think a little bit more if those are the same dichotomies in different forms, or
yes. So the existence of the description for both of the machineries are very much similar, right? Yes. That's something I agree.
Okay.
Yep.
I hear, I think a microphone has been turned on from somewhere else. Is there a question from the crowd here?
I hadn't turned on my microphone until just now, but I do have a question.
Okay, please.
I raised my virtual hand.
Can you just say who you are, introduce yourself before you ask the question?
It's Dennis Wilson here. I have a question about the sort of metaphor level that you were talking about that Turing considered in terms of the parent and the child, where it's sort of the computer that gives the calculation and that result is their child. I was wondering if you could talk about the difference between that formulation of it and what we consider now in sort of contemporary literature in terms of the learning of individuals and how that knowledge can be passed on between generations. Because it seems like those two metaphors are somewhat at odds. And when we want to consider a topic like the Baldwin effect, for example, and how information passes through generations, it's hard to do that in a framework where the information itself is the result of a specific generation.
Oh, yeah, that's an important question. And within this framework that I mentioned in this talk, I didn't really consider anything about the learning, right? So learning can be added on top of the physical construction process. And if we consider both the real physical biological replication and informational transfer, that's the co-evolutionary inheritance process that is actually going on in the real biological process, not only within humans, but also animals, and potentially even plants. They might be actually transferring some information from parent to offspring. So in that case, Jish, I haven't thought about it. How can we integrate that kind of informational dual evolution process inside it? Maybe we can consider the information transfer from one person to another as a separate yet interacting process of replication. For example, I'm doing this right now. I have some kind of computational process going on inside of my brain. I'm trying to brainwash everybody by giving this talk. So I'm now injecting some kind of the informational structure inside your tape, right? Everybody has a tape here. I'm trying to put the information there. So in that case, the ideas you are developing by listening to this stupid talk is the computed entity. And the idea I am driving myself with to inject those information is a computer, right? So the same argument might hold when we discuss information transfer from someone to someone else. It doesn't have to be parents and offspring. Any kind of information copying process could be considered also in this kind of format. But having said that, that there must be the very fundamental interrelationship between physical construction and the informational construction that is completely missing in this framework. And I guess you just pointed out the really important research question that you may want to explore. Did I address your question?
We'll see about that, but thank you. If I could just expand a little bit more on
please.
that.
Yeah.
How then do you see, especially in the context of work on the halting problem, the difference between learning and sort of knowledge acquired at an evolutionary level?
Is there any fundamental difference between those two?
Well, that's the question.
I don't know. The learning, we could argue that the learning is, in some sense, it's a very fast-paced evolutionary process that takes place within the very short period of time, isn't it? So we might be able to, describe both the learning and, acquisition of information through the evolutionary process. I think they might be fundamentally very similar process, unless I'm missing something important here.
I think there's different types of learning, right? There's sort of
different type of learning, yeah.
Like supervised and unsupervised, and some of those can be compared to evolution more effectively than others.
Yeah, but the evolution is also kind of supervised learning if you consider the environment as a teacher, right? So, or maybe it's unsupervised learning, and so is the information transfer also. It really depends on how you put the framework to consider the both processes. Okay.
Cool. Dennis, go. I just saw your hand raise. Is that the old hand raise that you did, or did you want to make another comment?
It's a new one, but
okay,
I don't know if there are other people who want to ask questions.
Okay.
So
go ahead.
This is more a question on the level of your work in looking into Turing's work and von Neumann's. There definitely are traces of the modern artificial life field in all of their work, and some of the work that you didn't mention in this talk were things like the work on morphogenesis that Turing did. And do you see those sort of ideas play into his work on the halting problem? And do you think that those things are still fundamentally linked today? I mean, this is potentially a biased question because, like you said on your introduction, you are an ALIFer at the base. But do you think that some of these questions that Turing approached, which can be considered fundamental computer science questions, still have an interesting ALIFE response to them that needs to be explored?
I would want to say yes. Yes. But the question, when you ask the question, okay, so how can we explore this? I have no idea. Right. So the basic direction of further exploration of this kind of topic is to find out, are there any other connections between the mathematical theoretical concept that was discussed back in the early 20th century, directly or indirectly connected to the modern biological concept that the people are already discussing, for example, right? So if we can find out any other potential linkages, such as the fixed point theorem, that is a functional mathematics, or any other stuff that might be very much related to for example, biophysicists or biomedical people are discussing. That, like, right now, we are struggling with how to cope with the coronavirus, right? It's a very fast-paced evolutionary process. And is there any mathematical structure to explain, or at least understand theoretically, what is happening? Is there any possibility to find out the stationary state of that kind of evolution process? So that might be the interesting connection that still has a very much current value to it. I'm not saying that solving that kind of the problem immediately gives us the benefit in the short period of time. I'm exploring these ideas completely without looking at any value. It's fundamentally curiosity driven, but which does not mean that this is totally useless. I believe there are ways to make a contribution to some real artificial life or biological studies as well. I think that's completely open-ended.
Great. Do we have any other questions from the crowd or comments? If people, yes, please, Pranjal.
Can you hear me?
Yes.
Just barely.
Okay. So my question is regarding whether this halting problem kind of thing applies to like real life, like living systems. For me, at least to my mind, cellular automata, like this game of life kind of construction, is more close to what we see like lifelike creatures behave, like Brandenburg vehicles, for example. And in that case, you don't exactly embody any like a halting scenario, like, halt when something is done. They just kind of evolve. There are some emergent patterns, but like not necessarily when to stop. So
yeah.
I had difficulty like connecting this. Can you elaborate maybe?
Yes, that's actually the great example. And one possible way to connect those different topics is to ask a question: why game of life, for example, it shows a very complex behavior, and if the space is large enough, it seems that they never fall into any periodic trajectory in the system. So one potential answer by after we realize the connection between the halting problem and this is that because game of life is computationally universal, right? So therefore, by definition, we cannot really solve whether or not the system's behavior is predictable. So the game of life itself is an undecidable system. And I would even argue that because the game of life is an undecidable system, that's precisely why it's interesting, and its behavior can go on forever. So there is a fundamental deep linkages between the decidability, undecidability, and the lifelikeness of the artificially created system, in my opinion. I know this is a very hand-wavy discussion. Many theoretical computer scientists watching this YouTube video would kill me, but it's okay. This is the inspiration-based talk.
Yeah, that's a good answer. Thanks.
Yeah.
We've got a question now from Bill Ross. Bill, you'll need to unmute yourself.
And I'll even show myself if I can manage. Can you hear me okay?
Yes.
Let's see. Looks like the camera isn't coming through for me anyway, but do you see anything?
No.
Okay.
It's okay. I can hear you. Yeah.
Yeah. It's no, it still says there it goes.
Oh, okay.
A little
Should I
color
put
here.
my camera also? So I can stop sharing my screen so that you can see me probably.
Oh, that's okay. That's
Do you see
okay.
me? Yeah. Hello.
Oh, there we go.
Yeah.
Cool. Wow. Right in my face.
I'm
my
alive.
camera's over here, so
Okay.
So when I'm looking at you, it looks sideways. Here.
Okay.
So
Yes.
now I'm going to look at you, really.
Okay.
So this is a little bit out of left field because partly because I haven't followed the whole thing. I came in at 35 after and wasn't even planning to contribute. But the notion of intergenerational transmission of knowledge came up. And and again, I don't have much foothold on what was said, but that is my particular project. So it just comes across as a plug, I'm afraid. But if anyone's heard of phobrain.com, PHOBRAIN, and wants to say we already know about it, say it now. But the idea is to possibly in the end create something like a Borgish thing that would sort of internalize people's minds and in a way that hasn't been thought of yet, but before me, but and somehow carry this wisdom over. My immediate goal is to create something that feels like a living. I'm looking you in the eye, and I know you must be looking at me, looking sideways.
Yeah.
Oh, I'm gonna drag it over so I can get a better feel to the laptop screen. All right.
Okay. Yeah.
So let's see. So my immediate goal is kind of like a philosopher. Oh, now I don't see you, but I assume I'm still around. Okay, it's sort of like a philosopher dog that can sort of intuitively teach the, you might say, the feeling-based, intuition-based reasoning that can support real intellectual reasoning, so that everybody has a better feel for things in terms of like statistics and logic and stuff than they do now politically, as we can see the trend going the wrong way. So anyway, if you're, it's based for now on the concept of Rorschach pairs, where I identify pairs that I like and dislike of pictures or don't care about. And so it turns out that simple neural nets can predict based on just color histograms alone up to about 80% accuracy of what I'm going to
sorry,
like.
Matt, do you want to say something?
I was just going to say, it sounds like it's getting a bit off topic for the actual presentation. So maybe it's something that you'd be interested in presenting on in another seminar or something like that.
Yeah. If you want to send me email or something, we can talk about it. But anyway, it's just to put a little pin on the idea of intergenerational transfer of knowledge in a very intuitive way as well as conscious.
Thank you very much.
So one more quick comment from me, if you don't mind. You had in one of your early slides, you don't need to bring it up, but just in one of the first points you were making, you're talking about human systems tending to create or less complicated systems than themselves. So you had this example of a factory building a car. And I wanted to try to sort of push back on that idea a little bit, right? Because humans humans also create societies and cultures and institutions that involve lots of humans involving in lots of very complicated ways. And so there's, I guess, two different ways I might try to push back. One is to say, well, how do we measure complexity? Because even this idea about life becoming more complex over time, a bacteria versus a human, there's an intuitive level where we want to say, humans are more complicated than bacteria. But and maybe there's some measures where that could be pulled out. But there's other people that might argue, especially in the ALIFE community, that's not an obvious one.
Yeah.
And then the other way to push back is, again, to point out these sort of emergent type systems, things like societies and cultures, and say that we do create things that are more complicated than ourselves. Do you agree with that?
Yeah, I would definitely agree with this. So the statements I made at the beginning of the talk is not my own view. It's actually the John Boynoy's view. And even though we agree that there are lots of different measurements of complexity, so we can't really say the humans are actually more complex than the bunch of the biomes. Like bacteria might actually have a lot more genomic information, right? But his question, based on my understanding, it is driven by some empirical frustration coming from the engineering side. Engineers always wanted to achieve something tangible, and it's more like a obvious goal that everybody wants. Not everybody, but some motivated engineers want to create designed artificial system that spontaneously evolves to be a more complex form. This is different from artificial society, because society is not designed, right? We participate as a distributed entities. As the population grows, the complexity of society also naturally grows. That is more like a natural side in John von Neumann's the contrasted picture. So he wanted to design and understand fully how to create. And that's pretty much artificial life approach. When you design a robot, can you make it more complex in the most intuitive sense? In the form that everybody agrees, hey, this one is coming out of that earlier stage and it is definitely more complex. regardless of the specific definition of measurement. So in this case, I think his question was very much empirically driven, right?
Mhm. Yeah.
And of course, he's a great mathematician, but another aspect of the greatness of John von Neumann is he's doing politics. He's doing all kinds of policy decisions. He also understands human complexity as well. So he never just stick into the mathematics, pure mathematics perspective. Otherwise, constructing cell automata is nonsense. But he did it anyway. So yeah.
There's another facet to both what Turing did and what von Neumann did, which to me is interesting in that it omits what might be described as sort of interaction with environment, right? Both of their abstractions are very, in a sense, isolated. There's a better word I can't quite summon, but yeah, they don't have an environment to interact with, and of course, ALIFers know well that complexity can come from that kind of interaction. You have a Breitenberg vehicle with this trivial brain controller, but you put it in a complex environment, and the behaviors that it produces can amplify the complexity of its environment. And so it seems to me like another interesting way that you might, you're transferring some stuff from life to these abstractions. It might be another avenue for interesting exploration. Yeah,
absolutely. And the environment can be other organisms, right? So it doesn't have to be the physical environment, or if the system is made of the whole bunch of diverse populations that could already, serve as the effective environment.
Yeah.
And I believe John von Neumann mentioned that later on in his paper. If the system is made of, the whole bunch of the similar self-replicators, there could be the possibility of evolution. So I believe he was aware, but simply back then there were no computers.
Right.
They are the ones who actually invented computers.
Yeah.
So without any computational power, it would be too much to consider the environmental interaction. In my opinion.
And then you get into like Langton's loops a little bit, right, where you do have these self-replicating machines surrounded by other ones. Yeah, interesting.
Yep.
Well, I think there was one more hand raise. Let me just make sure that there was only the one. It was from Dennis, and maybe this will be the last question for the day. So Dennis, do you have a comment or question?
I do, if it's okay. Just a last question, which was which came from this discussion about sort of the isolation of Turing and von Neumann's work. When you look at the literature at that time, it's very aspirational. It's very optimistic that what they are doing is universal. And I would say that there's a large difference with contemporary literature, where we have things like the no free lunch theorem, where we say, these things will not work in multiple different cases. And so when you look at that from a historical perspective, looking at that now in 2020, what do you think about the that sort of optimism that something like a universal Turing machine or a self-replicating system will actually be able to solve all of these different problems? Do you think that was realistic, or do you think that that was a bit exaggerated?
Yeah, so I don't think there's any universal solution to pretty much anything, right? I'm in that sense, I'm more like a complex system scientist who are very much pessimistic. The solution to any kind of problem is very specific, and the devils are always in the details. So when someone comes up, hey, we discover some universal methodology or universal solution, universal theory, I'm always very much skeptical about it, right? So the only situation where universality works is when we are studying mathematical constructs. And that's precisely where the Turing machines and the cell automata are perfect. No, they are not talking about the real world. And they are not really incorporating environmental interactions. And that's why they can say universal, right? And somewhat similar things can apply to statistical physics, where physicists always say universality class. That's a slightly different idea of universality, but still, it's an idealized theoretical model framework. But when it comes to the details, by the way, I was working on something similar related to this topic, if you start including the more realism, like diversity of behavior parameters, for example, the behavior of the macroscopic the property of a system is completely different from what would be predicted by assuming the idealized, stylized, model complex systems. So I think we should be very pessimistic about the possibility of universal solutions, but we should be very optimistic. That actually gives us a lot of research questions, because now we are shifting more to the specifics of each domain. And of course, we can still seek universal or at least cross-disciplinary similarities. That's where always interesting inspiration comes in. But now the research landscape is getting more complex. So we have plenty of open-ended questions that we need to address for specific combination of the research question and the realism. And that basically guarantees that there will be no shortage of jobs. Scientists continue to have more and more questions, but not in the theoretical computer science, because theoretical computer science was created by Turing, and immediately in the same paper, he closed it, right? So that is possible only if you work on theoretical mathematical framework. So that's my take.
Cool. That's great. Thanks for that response. One of my favorite things about the artificial life community is its ongoing engagement with these sort of philosophy of science questions. What kind of questions can we answer, or can we even ask properly, and how can we engage with them as science?
Improperly as well.
Absolutely. And informally. Yeah.
Informally,
Yeah. So, okay, thank you so much, Hiroki. Great talk, and thank you everybody who's joined in the live session, and thanks to you who are watching now on YouTube afterwards. Just as a reminder that the discussion can continue on the ALIFE seminars website, seminars.alife.org. I'm remembering that correctly, I believe. Yep, seminars.alife.org, and I hope to see you there. So, with no further ado, thanks again, Hiroki.
Thank you very much. Take care, everybody. Bye.
Bye. Okay, and I'll end the stream.